What if the most beautiful theory in physics isn't true? What if the key to everything, the unification of gravity and quantum mechanics, the secret language of the cosmos, isn't written in the vibrations of tiny strings, but in something else entirely? For half a century, string theory has promised to be the theory. A single framework to unite all forces, all particles, all of reality. Its mathematics is dazzling, its ambition unmatched. And for a time it seemed inevitable, the final answer hiding just beyond our reach. But decades have passed, predictions never came, and one by one, even its strongest supporters began to doubt. So, is string theory dead, or is it simply misunderstood? A theory ahead of its time, waiting for the tools to catch up. In this video, we're not here to ridicule string theory or to worship it. We're here to understand it, to explore where it came from, why it captured the imagination of an entire generation of physicists, and whether its promise still holds. Because buried beneath the equations and the hype is a deeper question. What do we really want from a theory of everything? Truth, beauty, or something in between? Long before it became a theory of everything, string theory was something far more modest and far more wrong. In the 1960s, physicists were wrestling with the strong nuclear force, the invisible glue that holds protons and neutrons together inside atomic nuclei. But they were doing it in the dark. The theory we use today, quantum chromodynamics, or QCD, hadn't been fully developed yet. There was no clear understanding of how quarks interacted or why hadrons behaved the way they did. Physicists were buried in experimental data. Hadrons, mesons, baryons, particle after particle, each with strange properties and no unifying explanation. They needed a breakthrough. In 1968, Italian physicist Gabriele Veneziano stumbled across a strange mathematical function, the Euler beta function, that seemed to match experimental data about how hadrons scattered off one another. It was elegant, it worked, but nobody understood why. Then came the reinterpretation. Maybe these particles weren't points at all. Maybe they were tiny, vibrating strings. In 1970, Yoichiro Nambu, Holger Nielsen, and Leonard Susskind independently proposed that the Veneziano model could be understood if particles were actually tiny loops of string, vibrating in different modes. Each vibration corresponded to a different particle, just like the notes on a violin string. It was beautiful, unexpected, and it had a fatal flaw. It predicted a massless particle with the exact properties of a graviton, a theoretical particle that, if it exists, would carry the force of gravity. But gravity has nothing to do with the strong nuclear force. That wasn't supposed to be there. So the theory was dismissed. It was elegant, but clearly not the right tool for describing hadrons. And yet, some physicists couldn't ignore the graviton. What if this theory wasn't just a failed model of the strong force? What if, by accident, they had stumbled upon something much bigger? A theory of quantum gravity hiding in plain sight. That's when the dream began. After its failed stint in nuclear physics, string theory could have been shelved forever, just another mathematical curiosity. But the graviton it accidentally predicted refused to be ignored, because if string theory naturally includes a graviton, then maybe it's not a mistake. Maybe it's a quantum theory of gravity, and that's something no one else had. In the world of physics, gravity and quantum mechanics have never played nicely. General relativity works beautifully on the scale of stars and galaxies. Quantum field theory rules the micro-world of atoms and particles. But when you try to merge them, when you ask what happens inside a black hole or at the instant of the Big Bang, the math breaks, singularities explode, infinities appear. For decades, physicists tried to unify the forces. Einstein died chasing that dream. But string theory offered something Einstein never had, a framework where gravity wasn't bolted on, fell out of the math, uninvited but perfectly shaped. The idea was audacious, that all particles, all forces, all of reality could be explained as vibrations of tiny, one-dimensional strings. The electron? A string vibrating one way. A photon? Another. A quark? Yet another mode. Everything, just music on the same invisible instrument. And it didn't stop there. To be mathematically consistent, string theory required extra dimensions, not just the familiar 3 of space and 1 of time, but 10 or even 11 dimensions, curled up in microscopic shapes called Calabi manifolds. Supersymmetry emerged as a natural consequence, every particle with a partner, uniting bosons and fermions. It wasn't just a theory, it was a vision. And when Edward Witten proposed M-theory in the 1990s, suggesting that all 5 versions of string theory were just different facets of the same underlying 11-dimensional reality, the dream reached its peak. Physicists called it elegant, cohesive, inevitable. It wasn't just that string theory could work, it was that it felt like it had to be true. But the universe doesn't care how beautiful your math is. And as the years rolled by, the cracks began to show. For all its elegance, for all its mathematical beauty, string theory has one glaring issue. It hasn't predicted a single thing we can test, not one verified experiment, not one confirmed particle, not even a rough prediction of a number we can go out and measure. That's a problem. In physics, a good theory doesn't just describe the world, it tells you what to expect. It risks being wrong. It sticks its neck out. Newton did it, Einstein did it, quantum mechanics does it every time we run a particle accelerator. But string theory, it explains a lot, but it predicts nothing. It tells us that particles are vibrations of strings, but doesn't tell us what those vibrations should look like at the energy scales we can observe. It tells us there are extra dimensions, but doesn't tell us how to detect them. It tells us there's a graviton, but we've never seen one, and we might never be able to. To probe the energy scales, where string effects would actually show up, we'd need a particle collider the size of the solar system. That's not hyperbole, that's the math. So string theory sits there, vast, complex, and silent, unfalsifiable, untouchable. And this raises an uncomfortable question. If a theory can explain anything, does it really explain anything at all? More and more, physicists began to ask, is this still science? Because if string theory can never be tested, if it can never make a prediction that risks being proven wrong, then maybe it's not a theory of everything. Maybe it's just a very pretty story. When string theory couldn't make testable predictions, some physicists thought maybe we're just not asking the right questions. Maybe there isn't one solution. Maybe there are many. As physicists explored the deeper mathematics of string theory, they discovered something unexpected and deeply fascinating. There wasn't just one version of the theory, there were trillions, and each version described a different universe. These weren't just minor variations, these were full-on alternate realities, different fundamental constants, different particle types, different laws of physics altogether. Some would collapse in an instant, others could never form atoms, but a few, just a few, looked a lot like ours. This vast collection of possible universes became known as the string theory landscape, a terrain of 10 to the power 500 different vacuum states, each one a unique solution to string theory's equations. The problem, if your theory allows for 10 to the power 500 different realities, it can explain anything. Why does our universe have the constants it does? Well, it just happens to be one of the lucky ones in the landscape. Why is gravity so weak or dark energy so small? Because we live in the valley where those things are true. This isn't a prediction, it's a post hoc justification, and to many physicists it felt like a change in direction. Instead of narrowing in on a single, elegant answer, string theory had exploded into a multiverse of possibilities, so many that any observation could be explained after the fact, which leads to a big question. If your theory can't rule anything out, is it even a scientific theory anymore? Some tried to salvage it using the anthropic principle, the idea that we observe this universe simply because we couldn't exist in most of the others. It answered the question, but didn't predict it. And so, the theory that once promised the ultimate unification of nature now seemed to dissolve into a sea of maybes. At first, string theory was the golden child of theoretical physics. It was elegant, ambitious, and, crucially, it wasn't quantum gravity's mess of infinities. It looked like the answer we'd been waiting for. But over time, questions began to build. Decade after decade went by, thousands of papers, countless conferences, and still no predictions, no experiments. No progress that the average physicist could actually test. Naturally, the honeymoon period began to fade. Discussions within the physics community became more open and passionate. Lee Smolin, in his book The Trouble with Physics, wondered aloud whether the field had become too focused on string theory, hiring string theorists, funding string theory research, and perhaps overlooking alternative ideas. Peter White, in his book Not Even Wrong, asked whether string theory still fit comfortably within the traditional definition of science. And Sabine Hossenfelder, known for her sharp insights, mused that maybe physicists were being guided by mathematical beauty rather than direct evidence, an idea that sparked plenty of healthy debate. And it wasn't just external voices. Even Edward Witten, one of string theory's greatest champions, acknowledged that the lack of experimental confirmation was frustrating. Some physicists, intrigued by new directions, began to explore other frontiers: quantum information theory, condensed matter, even philosophy. Because physics, at its heart, is about understanding nature, and string theory, for the moment, seemed to be focused on its extraordinary mathematics. Supporters reminded everyone that Einstein worked for years without data, and that general relativity took time to be tested as well. But others pointed out that Einstein's work made bold, testable predictions right from the start. And so the conversation began to evolve. What had once been a bold attempt to unify the universe was now seen by many as a beautiful idea, still waiting for its breakthrough moment, a theory brimming with promise, poised to one day reveal how it connects to the world we live in. For all its flaws, string theory isn't without its champions, and they're not fringe figures. They're some of the smartest minds on Earth. Because for all the criticisms, here's the thing. String theory works. Mathematically, it's astonishing, consistent, rich, unifying. In fact, it's the only known framework that naturally combines quantum mechanics and general relativity without collapsing into nonsense. It doesn't just include gravity, gravity falls out of it. That's not trivial. It's something no other theory of quantum gravity has pulled off with such grace. And the mathematical breakthroughs string theory has inspired, they've reshaped entire fields. Take the ADS-CFT correspondence, a discovery by Juan Maldacena in 1997. It showed that a theory of gravity in a higher dimensional space could be exactly equivalent to a quantum field theory without gravity in a lower dimension. That's not just cool, it's revolutionary. It's changed how we think about space, time, and even black holes. Or consider how string theory has deepened our understanding of black hole entropy, giving us a microscopic explanation for where black hole information might be stored. That's no small feat. It brings us closer to solving the black hole information paradox, one of the most haunting problems in modern physics. And then there's pure mathematics. String theory has predicted deep results in algebraic geometry and topology, results that mathematicians later confirmed independently. It's led to entirely new fields of mathematical research, bridging disciplines that had never touched before. So yes, string theory may not have delivered testable predictions about our universe, but it sparked progress in ways no one expected. To many of its defenders, the lack of experimental proof doesn't mean string theory is wrong, just that it's unfinished, ahead of its time, waiting for the right tools, the right technology, the right questions. They argue that progress doesn't always come in the form of experiments. Sometimes it comes from ideas that take decades, or even centuries, to mature. After all, it took nearly 100 years to test some of Einstein's predictions. So maybe, just maybe, string theory needs more time. While string theory dominated headlines and faculty positions for decades, a quiet rebellion was growing in the shadows. Other physicists, tired of the elegance without evidence approach, began exploring alternatives. None as famous, none as mathematically grand, but maybe more rooted in reality. Loop quantum gravity, LQG. If string theory is the opera house of theoretical physics, loop quantum gravity is the garage band. Less glamorous, but fiercely committed to the basics. LQG starts from a simple premise: take general relativity seriously, but quantize space itself. In this view, space is not continuous. It's made of tiny loops, like a woven fabric. Time and geometry emerge from these discrete chunks. It doesn't require extra dimensions, no supersymmetry, no strings. And it actually makes falsifiable predictions, like a minimum volume of space, or slight deviations from general relativity that might one day be observed in cosmic background radiation. But it struggles with unification. LQG doesn't naturally include matter particles or explain why we have the standard model. It's more modest in scope, and that's both its strength and its weakness. Causal set theory. This one is radically minimalist. It suggests that spacetime is fundamentally discrete, a set of atoms of spacetime linked by cause and effect. No strings, no loops, just a growing network of events. It's simple, clean, and it respects the causal structure of relativity. But it's still highly speculative and has struggled to make contact with known physics. Asymptotic safety. This idea, championed by Nobel laureate Steven Weinberg, proposes that gravity might be safe at high energies, that it flows to a fixed point rather than exploding into infinities. It's a quantum field theory of gravity that doesn't need strings or new dimensions. The math is tough, the predictions are subtle, but it's a serious contender, especially because it doesn't throw out everything we already know. Emergent spacetime and holography. Then there are the wildcards, approaches that suggest spacetime itself isn't fundamental, but emergent. Ideas from quantum information theory, tensor networks, and the holographic principle are painting a new picture, that reality may be encoded on lower dimensional surfaces, like a cosmic hard drive. These ideas often intersect with string theory, but they're also carving their own path. A path where gravity, time, even space might not be what they seem. None of these rivals have won, none have unified all the forces. But that's the point. For the first time in decades, physics is no longer dominated by a single idea. The field is opening up, growing diverse, willing to explore again. Because maybe the road to truth isn't through one grand theory, maybe it's through many smaller ones, each revealing a piece of the whole. Science was once simple. You had a theory, it made predictions. You tested those predictions. If they were wrong, the theory was wrong. Rinse and repeat. That's the Popperian model, named after philosopher Karl Popper, and it's been the gold standard for centuries. The heart of it? Falsifiability. a good theory must risk being proven wrong. But what happens when your best theories can't be tested at all? String theory, with its extra dimensions, unreachable energy scales, and vast landscape of possible universes, doesn't make predictions in the traditional sense. Not because it's vague, the math is extremely precise, but because its predictions lie forever beyond our reach. So does that mean string theory isn't science? Some say yes. If a theory can't be falsified, it doesn't belong in the lab. It belongs in the realm of metaphysics or mathematics. That's what critics argue, that string theory has become a kind of high-level theology, beautiful but unprovable. Others disagree. They say the falsifiability standard is outdated, that science isn't just about experiments, but about explanation. If a theory unifies known laws, guides future research, and provides mathematical coherence, then it's doing real scientific work, even if we can't test it yet. There's also Thomas Kuhn's perspective, that science moves in paradigms. Sometimes we work within a model that hasn't yet delivered results because there's nothing better. Progress comes not from strict logic, but from shifts in worldview. So maybe the question isn't, is string theory science? Maybe it's, are we ready to expand what science is? Because string theory forces us to reckon with something uncomfortable. The universe might not care if we can build an experiment. Truth might be stranger and harder to test than we ever imagined. And that leaves us standing at a crossroads. Do we cling to the traditional model of science? Prediction, test, repeat? Or do we admit that some truths might only be seen in the math, not in the lab? So, is string theory dead? Not quite. It's wounded, it's drifting, maybe even lost, but not dead. Because even now it continues to inspire, it continues to reveal unexpected links between gravity, quantum mechanics, information, and geometry. It continues to evolve, often in directions no one predicted. It may not be the theory of everything we once hoped for, but that doesn't mean it was a waste. Physics doesn't move in straight lines. It stumbles, it circles, it revisits old roads with new eyes. String theory might not be the final answer, but it might have been the question we needed to ask to get there. And maybe that's enough. Maybe the legacy of string theory won't be a grand unifying equation, but the realization that the universe is more subtle, more complex, and more beautiful than we ever imagined. In the end, the dream of a theory of everything is still alive, but we're learning something humbling. The truth doesn't always fit inside our theories. Maybe the universe doesn't speak in one voice. Maybe it whispers in many. But maybe our job isn't to find the final answer, but to keep asking better questions. Because in the end, physics isn't just about particles and equations. It's about the mystery and the courage to chase it. The universe is vast. Let's explore it together.